I'd like to share what that loss function looks like in code. But before I can, let's talk about the other key insight DeepMind had with their Atari breakthrough, which is called experience replay. Instead of training after every step like in TD learning, we're first going to collect the state transition in a memory buffer. Once we've collected enough memories, we'll pull out a sample batch and train on that. The way this works in practice is with each time step, we get a bunch of information to train on. We'll create what's called a memory buffer. Every time we complete a cycle, we'll append our training information as a row in the buffer. In Python, the buffer is usually a deck, so when the buffer is full, older transitions are dropped out, just like how older memories become forgotten. Once we've gathered enough memories, we can start training our neural network. We'll take a uniform random sample across all the memories and turn that into our training batch. Let's build out a memory buffer so we can get a sense of how this works in code. First thing we'll do is initialize a class that takes in a memory size, which is the size of our buffer, and a batch size, which is how many memories we want to sample when training. Then we need a method to add an experience to the buffer. Python Dex has a handy append method, which will automatically drop older memories when the buffer is full. Finally, we need a way to sample from the buffer. NumPy's random.choice function is useful here. We can give it the batch size and tell it the sampling pool does not replace values that are sampled from it, so we can get a nice list of unique elements. This memory sampling technique was a big advantage for a few reasons. The first is that we can recycle memories for training, which is great because simulating experiences can be expensive. The other advantage is that we can decorrelate experiences. You may have already heard why shuffling is important in supervised learning. If we don't shuffle, our gradient descent is likely to train on a batch that's not representative of the full population loss curve, and we may accidentally push our training to a local instead of a global optimum. The same is true here, but there's an extra disadvantage to not shuffling experiences. Our agent learns based on its previous choices, so if it's training towards a local optimum, when it comes time to select an action during simulation, it will tend to pick actions based on that local optimum, further pushing it away from the globally optimum strategy.